All right, hello everyone. I'll be presenting. My name is Rundong Tian, and I'll be presenting on behalf of my collaborators, Vedant, Mareike, Florian, and Paulos. So the high-level question guiding the work that I'll be presenting today is how can a fabrication tool capture both the ease and fluidity of manual fabrication, as well as the accuracy and repeatability of digital fabrication? So diving into that question a little deeper, our approach isn't about making digital fabrication more embodied, but to start at the other end of the spectrum with hands-on fabrication, where we can already work with tools fluidly and directly. And from there, we can think about how we can weave in the capabilities we typically associate with digital editing. So imagine for one of these hands-on fabrication tasks, being able to have things like snap to grid or copy and paste. So we're interested in fabrication broadly, but to begin to explore and implement these ideas in detail, we choose one particular fabrication tool, in this case, a lathe. So lathes are especially good for making cylindrical geometries, like these objects we made using our system. In addition to being practically useful, they're often called the mother of machine tools. So very generally, this is how a lathe works. The black cylinder is the material being cut, and a cutting tool is translating on a two-axis gantry. And here, I'm using one of these dials, or hand wheels, to control each axis of that gantry. And this process is commonly referred to as turning, hence our title, Turn by Wire. And backing up a bit, looking at the differences between a manual tool like the one on the left, which are also driven through hand wheels, to a modern-day CNC lathe, there's this huge shift in workflow and what the role of the operator is. On the right, when you're at the machine, it's almost less about making and really pressing the right combination of UI buttons to replay a toolpath. And of course, the jump from manual to CNC lathes is really representative of digital fabrication in general. And one limitation of these CNC workflows is that in order to interact with the capabilities of a tool, you now have to interact with this, you have to traverse this gauntlet of software packages that can be oftentimes inflexible, indirect, and disembodied. And these limitations are certainly ones that the UIST fabrication community is familiar with. To give a brief sampling of the many approaches that have been explored, handheld tools have been augmented with additional actuation, sensing, and knowledge of some digital model. Projects in interactive fabrication have also aimed to achieve more direct interactions with fabrication tools, but without necessarily being literally handheld tools. And because those work often exhibit turn-taking interactions, projects have further examined how to tighten those interaction loops. And lastly, critical works have been proposed which explicitly set out to reclaim agency over the fabrication process. What I think of as one of the most interesting pieces of related work actually came much earlier, and that's with something called record playback, which was developed in parallel with full numeric control in the mid-20th century, really at the dawn of digital fabrication. So this early vision for digital fabrication addressed many of those limitations directly. Record playback did just that. The system recorded a machine's actions as they're cutting as a means to generate the tool paths that can be played back automatically. And because it's still a manual tool, the way that you generate the tool paths is more direct, more flexible, and leverages the existing embodied knowledge of the people who operate these machines. Not to mention that you get the part immediately after, quote-unquote, programming the toolpath. And we see this tool being situated in this really interesting space between digital and physical fabrication. It's still very much a manual tool, but overlaid on top of it, we have some capabilities that we would typically associate with digital editing. So they called it record playback, but we can think of this as copy and paste. And there's no sense of turn-taking or tightening interaction loops, because the physical act of machining is the process for designing the toolpath. And it's also, if you're working with it in this more fluid, direct way, it's also the process for generating the model for the design in context of the manufacturing constraints required to make it. So working from this early alternate vision of what digital fabrication could be, we're also interested in thinking about how sensing, actuation, computation can be a means to complement and augment human capability during the process of fabrication, rather than as a means to automate that process entirely. So we're very much starting from physical fabrication, but thinking about how computation can complement and mediate that experience. The main idea behind our system is that we keep the manual control, but have the coupling done entirely by wire. So instead of a mechanical coupling, like a mechanical transmission, we have this programmable coupling that buffers the user and the tool. And the coupling that we created is bidirectional. We modulate both the position that the user commands, as well as the forces that the lathe wants to communicate. And because these hand wheels are really context-specific modality, we complement that with a general-purpose graphical user interface for doing things such as tool selection or modifying settings. So we leverage turn-by-wire control towards three primary themes. The first is intent. How can design intent be expressed more concisely? how could the system capture the most salient aspects of the design to really go beyond what a manual tool could do? The second theme is complementary, the inverse of the first, and that's about perceiving state. How can users understand how their work is progressing? Fabrication tools aren't necessarily these static objects that we can impose design will upon, but should also inform us about their capabilities and constraints. Lastly, we have scaffolding, which is a more specific type of feedback. How could the tool inform the user about technique, and how could the tool teach the user how to use it? So earlier we alluded to snap to guide, and in our system, users can set a virtual haptic guide through the graphical user interface, and then the hand wheels physically snap to those guides through haptics when the tool approaches the predefined dimension. And here, it's this really lightweight way of capturing something we typically associate with CNC machinery, automatic accuracy. And we also see how the forces that are being rendered aren't necessarily real or literal, but communicate these additional layers of information that weren't previously there. Next, suppose you want to cut a radius. You can use something like a virtual tool on our system. So when the virtual tool is activated, a single hand wheel now moves the tool along an arbitrary path rather than its original designated axis. So instead of using a specialized jig or coordinate multiple inputs simultaneously, we can remap the coupling between the hand wheel and lathe and software to expose controls that most succinctly captures the most important aspects of a design. And we've also revisited record playback. So in the top right corner, you can see an interaction similar in style to some end-user automation tools. For example, the Actions panel in the Adobe suite. And after the action has been recorded, the toolpath can then be reviewed and replayed. So this way, if you need another copy, or if you made it in a way that you particularly liked, you don't have to repeat yourself if you don't want to. The second theme is perceiving state. So state is communicated continuously through haptics. While cutting, users not only control position, but feel a simulated reaction force proportional to the amount of material being removed. And the reasoning for this is that the first indication that something might be going wrong shouldn't be that the tool breaks or your part breaks. It's that, it's that you should be able to feel that change immediately. And the coupling is not fixed. When you have a delicate tool, you can imagine amplifying, if you have a delicate cutting tool, you can imagine amplifying those forces. Or if you've developed a sensitivity to the tool, you can imagine attenuating those forces. Lastly, how could the system teach the user how to use it? There's a really wide range of lathe tools and varied techniques around how to use them. And in this example, the system is enforcing best practices for drilling. So rather than to cut to final depth in one go, the system is encouraging the user to peck at it incrementally. So the hand wheels do that by physically resisting the user's input to show that the cut material should be cleared out first. And this is just one technique that our system supports. So far, we've talked about turn-by-wire as very much this black box. And here I'll briefly discuss the architecture. But for more details, please feel free to ask me during the question and answer or to take a look at our paper. The main takeaway is that it's hierarchical. We have microcontrollers which interact directly with the hardware to give us the timing regularity of real-time control loops for doing things like the haptic feedback. But then we expose interfaces that can be coordinated by high-level programming language to develop these interactions. So here, most of the logic is running on client-side JavaScript, and the latency between the web browser to the hand wheels or to one of the pieces of hardware and then back again is on the order of 10 to 20 milliseconds. In terms of the hand wheels, the mechanical design references the configuration found in a traditional lathe. The haptic controller is a motor with an encoder acting as both the sensor and actuator. And for the haptic rendering, we use a combination of electronic braking for passive feedback, as well as an impedance controller for active feedback. So to probe reactions to our system, we recruited 5 expert users in a preliminary user study to create a simple component using turn-by-wire. And for the participants, we conducted a really targeted recruitment from the expert staff of an educational makerspace who were deeply familiar with both manual and CNC tools. And the reasoning behind this was that we hypothesized that they would offer interesting insights into how and why these particular tools might be useful by contrasting it with their existing practices. Because this is by no means a new machine, it's in fact one of the oldest machines that humans have invented, but the differences are in how you interact with the capabilities as well as the workflows supported. The component we chose exposed users to all of our haptic interactions and requires many of the most commonly used lathe operations. And all 5 participants successfully created this widget within 15 to 20 minutes after a 15-minute training period. And you can see the 5 pieces on the right there. So after the participants finished machining, we conducted a semi-structured interview as well as gave them a link to an anonymous questionnaire which they answered offline. Okay. Next, I'll share some results from the interviews and questionnaires. And I'll use the questionnaire responses to help structure our discussion. And first, I'll share some responses specifically about the haptic feedback, starting with the least positively rated, which was technique scaffolding, where 4 participants agreed that it was useful and 1 participant agreed that it was, strongly agreed that it was useful. And this may have been due to the high level of initial familiarity that our participants had with lathes. And many indicated that they had already had experience with lathes, as well as knew how to use these different tools. At the same time, in the interviews, one participant conceived of our system as a CNC machine to teach material considerations, how to feel material. And here we kind of see the strange irony of how CNC machines were originally designed to remove the need for human intervention and judgment, but here with minimal modification can be used to do the exact opposite. The most positively received haptic feedback feature was Snap to Guide, where 4 participants strongly agreed that it was useful and 1 participant agreed that it was useful. Participant 5 said, the ability to set the limits so you don't cut too far and actually helps you make the exact dimensions you want. That sets it apart from any other machine. Just a manual machine or digital readout, a DRO, doesn't physically stop you from going past those limits. So again, we see how these haptic guides are this lightweight mechanism to achieve something we typically associate with CNC machines, which is automatic accuracy. Many of our participants also appreciated the emphasis on machine feel. Participant 4 said, my favorite thing about this so far is the machine feel. It's so difficult to communicate to people what it should feel like. So while phrases like monkey tight or gorilla tight try to capture embodied knowledge and the subtleties of touch, but here we have a system that can communicate that information explicitly and directly through haptics. However, not all participants could feel the difference between cutting a lot versus a little bit of material, and we interpret this as the settings for the force feedback gain may have been too low to discern any important differences in cutting force, but because of the by-wire coupling, these could be further tuned in software. And next, I'll share some overall responses to how this tool was perceived. So many participants were surprised by how easy it was to learn. So participant 1 said, it was a lot more comfortable than I expected because in the beginning you told me it's kind of like a CNC and I thought the learning curve is going to be bigger than what just happened today. And this was a sentiment echoed by a lot of our other participants. So even for expert users who are really familiar with CNC machines, it doesn't mean that learning a new CNC workflow is necessarily less opaque or easier to use. And when prompted about using manual or CNC tools with the same capabilities, we had a really interesting mix of reactions, with some users saying that they would prefer this tool over a manual tool with similar capabilities, and others saying that they would prefer this tool over a CNC tool with similar capabilities. So probing this liminal space further, when asked whether or not the participants thought of when we probed them explicitly about whether they thought turn-by-wire was a hand tool or a CNC tool, the responses were also mixed. One of the participants who was really excited about this tool said, I feel like it's right down the middle between hand and CNC. If I'm trying to do a hand plane and it's not cutting, it's either the way I've set it up or my technique. But here there is that kind of black box with a question mark on it between me and the operation of the lathe. So the turn-by-wire architecture enables these interactions, enables these new interactions, but we do introduce a level of ambiguity compared to a true manual tool. So in ongoing work, we've started to explore visual augmented reality as a way to complement the haptics, which can be already thought about as augmented reality for touch. And here we see how there's a component loaded visually, but none on the actual lathe. So to summarize our discussion today of bringing capabilities of digital editing for physical fabrication, we started with this really interesting example from the dawn of digital fabrication, where copy and paste was introduced for a physical fabrication task. And building off of that, turn-by-wire enabled other interactions as well, such as Snap to Guide or virtual tools. And I want to emphasize that there's many more digital capabilities that can be explored, as well as other tools to explore them on. So for example, we can have autocomplete, undo, redo. Within record playback, we can explore things such as trimming, filtering, or smoothing. But revisiting our initial motivation to experience digital editing to experience the capabilities of digital editing for any physical fabrication task, we're interested broadly in how turn-by-wire control can be coupled to us directly, as well as these context-specific tools. And this could be achieved through things such as robots or ungrounded force feedback. With that, thank you all for your time and attention, and I'd be happy to take any questions.
All right, who's got questions? Put those hands in the air.
Thank you very much. Michael MITC's here. So like when you are like interacting like, with these tools directly, so with automediation, you get like some channels of feedback from it. So like they have this force feedback, but I could also like imagine the smell, the vibration of the material. Like what kind of channels do you think like would be interesting for the system?
Yeah, absolutely. So it's like, yeah, if, right, let me just rephrase your, yeah, absolutely. When you're working with a manual tool, there's a lot of different, there's sense of sound, there's sense of vibration, there's even sense of smell if something's really going wrong and it starts to burn. But those things aren't typically things that you can pick up immediately after starting to work with the tool for the first time. You have to kind of develop your sensitivity towards these different things. And yeah, absolutely. I think, yeah, sound especially can be explored in future work and thinking about kind of amplifying those a little more so that novices can pick up on those signals easier. Yeah.
Anybody else have a question? Oh.
Hi, this is Jian Kim from Texas A&M. So how can undo be done once the user already cuts away all the materials?
Yeah, absolutely. So I think there's a few ways, practically speaking, to implement undo redo. So we have something, so we have the record playback, and right now it's being triggered manually by the user. But you could also imagine a different infrastructure where it's always recording in the background. So if you make a mistake, then you can say, oh no, let me either reload something and replay until that last point where I didn't make a mistake, or say, okay, I'm just going to keep going, but on the next one I want to skip this part where I messed up. Yeah, so those are maybe two practical ways to get at it.
Anybody else with a question?
Hi, I'm Emily Whiting, Boston University. I was wondering if you found any instances of divergence between how the object was fabricated and the expectation of the fabrication, and if so, if there was a need, for instance, to have a computer vision system checking that the prediction and the actual fabrication was progressing in the correct way.
Actually, could you repeat your question? Sorry.
So by divergence, I mean that a cut was supposed to have a certain effect, but did not have exactly that same effect when you actually applied the action.
Right. So for example, something like the snap to grid, like we're assuming that everything's perfectly calibrated, and in that perfectly calibrated world, once the hand wheels get to a certain point, then that cut should be a certain point. But I think, yeah, with additional sensing, like we can direct, rather than being able to snap to guide in terms of having that original ground reference be like a limit switch, we can imagine other sensing to say, oh, it's not snap to the open loop, whatever 16 millimeters is, it's like now snap to loop to actually that dimension that's being measured in real time. Yeah, absolutely.
Okay, thank you guys very much for your questions. And if we could thank Rundong again.